We spent a lot of time dealing with conservation of mass. Now we need to deal with conservation of energy and get that energy equation. Once we have that energy equation, it's apply, 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 apply. Apply it. One general equation that's applicable to many situations. We derived last time the mass balance equation. Let me do a quick cliff notes on that, because the same strategy is employed for the energy, it's just more tedious. So what we did was we said we know we have flow coming in and going out. What we'll do is we'll look at a snapshot in time. We'll call this time t, and this time t plus delta t. And at time t, we'll decide on a fixed amount of mass. Some of it has not entered the control volume yet, but will shortly enter the control volume. And then everything that's in my control volume, and so we define our control volume is this. That's our fixed region in space. It doesn't have to be a box, but I show it a box. And this is about ready to enter. We'll call that the mass about ready to come into the control volume from the time t to the time t plus delta t. So the mass that's purple deforms. It looks like this shape at time t. After time t plus delta t, it's in this shape, which means some of that deformed and pushed out of the control volume is exited the control volume. This is the mass that exited. So for conservation of mass, what we say is the amount that is our focus of our study, our closed system, which is deforming, our closed system is the mass at time t plus delta t is equal to the mass at time t. Well, the mass at time t plus delta t is made up of two parts. It's made up of the mass that's in the control volume inside the box at time t plus delta t plus the mass that just exited. This part and that part make up the mass. It's also, if you look at the mass at time t, it's made up of the mass in the control volume at time t. That's this part, right? Plus the amount that's affixing to, how do you like that for a word? That's only in Texas, right? Fixing to, is that South Texas, East Texas? I don't know. We're fixing to, it's a fixing to coming to that control volume, mi. So we rearrange, we write mass control volume t plus delta t minus the mass in the control volume at time t is equal to the mass that's about ready to flow in during that time interval minus the mass that flows out, exits during that time interval. We divide the whole thing by delta t, delta t, delta t. We do some name calling, some observations. This is the rate of change of the mass in the control volume. It's equal to the rate at which it flows in minus the rate at which it flows out. Do you recall that? Good. Now you just extend it a little bit for energy. Same principle. Okay, I know I'm going to run out of room, but let's try it. So instead of talking about the mass at time t plus delta t, we talk about the energy that's in this fixed chunk of mass at time t plus delta t. The energy that is at the same chunk of mass at the earlier time. Well, how could that energy have changed in our chunk of mass? By a Q and by a W. And our W is net out, positive out. Our Q is positive in. That's why there's a negative on that W. That's a first law for a closed system. This closed system is deforming from time t to t plus delta t. So let's bust up this amount at time t. That's equal to energy in the control volume at time t plus delta t plus the energy that's fixing to exit. Expand this energy at time t. That's the energy inside the control volume at time t minus E that entered, that came in, Q. You see what we did on that? trying to save some room because I want that CV term so I can divide by delta T and turn it into time rate of change of energy in the control volume. Now, the Q, I'm just going to leave its Q in. Yes, sir.
Can you go over that part?
Okay. This one went to these two parts. And this one went to those two parts, and I had to be careful with the minus sign. And so the energy at time t is made up of just this part plus that part. And the energy is at time t plus delta t is made up of this part plus that part. Now I have to work on this work term. The work I'm going to separate into a shaft work that cuts across the control volume. The work, and I'll put a CV on there. That's different than the W without, because the W without a subscript can include boundary work, which is pushing in or pushing back. All right, now I have two boundary works. I have a boundary work, that's why we model it like this piston. Let's do the first one, which is positive from the perspective of the system. The system's pushing this piston back. It's a positive boundary work. We're going to put in here a positive work as it exits. Boundary work pushing back on that big piston on the exit. Minus the work on the in. And I just barely had enough room. Now, luckily, I'll just expand this. Energy CV at time t plus delta t minus energy CV at t, leave that as a group, equal to Q minus the work control volume. It's going to be a minus WE, a minus E sub E, plus a WI for in, plus E sub I in. All right. If you allow me, let me do one more thing. I'm going to back up. I'm going to change these subscripts. And I'm going to put this positive, positive, in, negative, negative, out, out. Just trying to put it into the terms so it's going to look like our final equation when we get there. This work, the boundary work, is the integral P dV. Well, it's a constant pressure pushing it back, so it's the pressure on the inlet, the inlet over here, this pressure on the inlet, times the volume that it was moved. The boundary work is the integral P dV, constant P, it's just a PV term. Okay, the same with this pressure on the exit, volume at the exit. Now the other one that I do is you say, well, what is the volume? I know that the mass came in, but can I get an expression for the volume that that mass occupied that flowed in? Sure, that's equal to the mass times specific volume in. So I could replace look at that, PV showed up. There's that PV term. I'm going to lump that with U and get H. Over here, P exit, V exit, mass exit. So I focused on the two boundary works for a couple steps here. We have the energy in the control volume at time t plus delta t minus energy control volume at time t equal to Q minus W control volume. Then this energy term here, E sub I, the energy associated with the mass that flows in, is that equal to the mass that flows in times U sub I plus 1/2 VI squared plus GZI? It is. And I'm sorry, I got these kind of little messed up. This is PEVE. That one goes here like that. So that's a minus sign, minus the mass that exits times its internal energy that exits, plus 1/2 V exit squared plus GZ exit. Ugh, almost didn't make it. It's really sloppy, isn't it? Sorry about that. So if you divide this by delta t, divide by delta t, divide by delta t, These terms all come together and you divide by delta T. These terms come together, divide by delta T. What we pick up is finally the rate of change of energy in the control volume with respect to time is equal to the rate at which it flows in by heat. Put a dot on that Q. It's Q dot. It's not kilojoules anymore. It's kilowatts flowing in minus Q, the W dot CV. And yes, it's important to go ahead and put it. It's cutting the boundary of the CV. It's not a boundary work. It's a power associated with like shaft or maybe electrical power, some energy flow that's not heat transfer. Typically think of a shaft. That's conceptually pretty straightforward. Now this one, we have the mass flow rate in. So this grouped like that. And what we're left with is U in plus PV in plus 1/2 V in squared plus GZ in. And then over here we have, just like that, mass flow rate exit times U exit plus PV exit plus 1/2 V exit squared plus GZ exit. We call this group of terms H. Enthalpy. Enthalpy is U plus PV. You have it on the inlet as well as the enthalpy at the exit. Enthalpy is not something special. It's just a rearrangement. And they said this group of parameters occurs so often. Let's give it a separate name. Let's call it enthalpy. Yes?
So if the boundary expands...
Okay. Thankfully, in Thermo 1, our control volume is fixed in space with time. But you're right, it could expand. And now that's the one the physicists love and great. Do you want to put it in toroidal coordinate systems, would you? You know, make it as hard as possible so you can't see it and use it. Thankfully, our control volumes are fixed in space. A good observation, thank you. So guess what? This is our new equation. There it is. I tried to keep it in the same shape, form. The rate at which energy is accumulating or being depleted. If it's positive, if this term is positive, that means the energy is being stored more and more with time. It's increasing. It's like your bank account. Money's going up, 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 right? You're going to own the bank soon. Maybe not. This is the rate. There is a dot on top of this. The rate at which it flows in across the boundary of the control volume in the form of heat. This is the rate at which it flows out across the control volume boundary in shaft or electrical or some other organized work, but not boundary work. This is the combination of internal plus flow work, PV. That you think about that flow work, that piston, imaginary piston pushing in or being pushed out. That PV is flow work. Internal plus flow work makes enthalpy. We have the kinetic, we have the potential energy coming in. It's coming in at a certain rate with the mass. The mass is carrying it. Can I have the inflow of internal energy without a mass transfer? No, maybe a heat transfer, maybe a shaft work, but if your kinetic or potential or internal energy is coming in, it's coming in with mass. It's a property of the mass. Mass is, bringing it in. And it's going out with the exiting. Oh, now I just don't have one pipe coming in. I have multiple. Do a sum. Do a sum. You have 2 pipes, sum them up. 3 pipes, sum them up. Oh, I have 5 exits.
I just can't picture. What would an example of electrical work be? I can picture a shaft.
Sure. We have a duct and it has an electric heater in here. And so the duct will have an inflow and an outflow, and we'll do a control volume right here. So the duct is insulated, and so there's no heat transfer. But we want to account for this electrical energy coming in. We'll call it electric power in, which would be a negative. See here, if it's coming in it's negative
Right.
for our
Is there
sign.
a way to get out that way?
You have a big control volume. Let's say you have a steam turbine and it's hooked up to an electric generator, and steam is coming in and steam is coming out, and I'll put a big control volume, which includes the turbine and the generator, and now I have the electric coming across the boundary way over here on this side. Now we apply this energy balance equation for an open system, for a control volume, to numerous applications because it's so general. To a nozzle, to a diffuser, to a turbine, to a compressor, a pump, heat exchanger, throttling device. I know I went through that list fast, but you should start to get a grasp. What is a nozzle? What's its purpose? Is there heat transfer or typically not heat transfer with it? Is there a work with it, not a work with it? Is there more than one inlet, more than one outlet? Typically, they run at steady state, and there's typically one inlet and one outlet for the mass flow rate. So airflow through an adiabatic nozzle. Let's just jump into a nozzle problem. When you see air, typically you think ideal gas. It flows through an adiabatic nozzle. That word means something, adiabatic. No heat transfer, Q dot 0. It's a nozzle. It's basically reducing cross-sectional area as it flows through. A lot of times we draw a control volume like this. There's my control volume for the nozzle. It flows in across this boundary over here. We'll call it 1. It flows out across this boundary, state 2. State 2, 1 and 2. Inlet 1, outlet 2. It enters at, oh, they give me a pressure. Pressure at 1, 300 kPa. Temperature at 1, 200 degrees C. And you know what? Since I probably am ideal gas, I may need to use PV is equal to nRT. Slap a 273 on it right away. So if I need it in Kelvin, it's 473 Kelvin. It's coming across with a speed of 30 meters per second. That means they're trying to give you a hint. Don't neglect the kinetic energy. Include it in the calc. Okay? 1/2 V squared is the specific kinetic energy. Then that's through the cross-sectional area. Oh, they tell me the area of 1 is 80 centimeters squared. That's how big the inlet is, the cross-sectional area. It exits at P2, 100 kPa, and a V2. Sometimes I'll try and arrange it like this. V2 is equal to 180 meters per second, meaning I left blank T2, I don't know that. I left blank A2, I don't know that. See, I left kind of a space for it. All right, determine the mass flow rate through the nozzle. Then determine the exit temperature of the air, and then determine the exit area of the nozzle. One of the things you do when you read a problem like this is you reread it, and then you organize information just like I did with a sketch. And then you try to keep the information in order such that it helps you. And then I finally see, what do I need to calculate? Introduce a symbol for what you need to calculate, and if you need a subscript on it, put a subscript on it. So what's a good symbol for what you're looking to calculate for A? M dot. Should it be M dot 1, M dot 2, or just M dot? You do the conservation of mass so quick. There's no accumulation, depletion of mass or air in this nozzle. It's just running. And so M dot in is equal to M dot out. There's only one in, one out. Boom, you're done. It's just M dot. You don't need to put subscripts on M dot. It's just one variable. What about exit temperature of the air? T2. That's what I'm looking for. Sometimes I'll come over here and I'll put just temporary, I'll put some question marks like, hey, I don't know that and I need to calculate it. How about exit area of the nozzle? A2. And look it, I've lined this up and I've lined that up. True? Okay, it's just helping me try to organize things. My style, maybe I don't want the question marks there. Sometimes I do. What does this down here? Use C sub P is equal to this value for air. What are they telling me?
Ideal gas.
And it's not only an ideal gas, it's constant specific heat. So if I need to calculate the change in H for it, it's C sub P delta T. True or false? True. Even though the pressure changed, is the change in enthalpy purely only dependent on the change in temperature? Yes, it is. All right, so now what do? So we're using a constant value of specific heat. What is the mass flow rate? Well, if I could calculate the mass flow rate coming in, then that's the mass flow rate, true? Is the mass flow rate equal to rho in, area in, speed in, rho AV? Good. Is it also equal to A1 V1 over specific volume 1? Sure is. Either way you like to do it. So we go back and we say, I know that some of this information is not given. So does it say anything about a transient behavior here? Any word saying, oh, this is a transient nozzle problem? No. Does it say explicitly, oh, you can assume it's steady state? No. I may want to make an assumption. I'm going to just assume it's steady state. Or you just solve these problems so often you know, hey, it's steady state. All right? But you could probably make a little list over here. Assumptions, steady. If it's steady state in the ideal gas, it didn't ever say that air could be treated as ideal gas. You can confirm it or you can just assume it. Either way is going to work. So what is rho 1 is equal to, or specific volume 1? How do I calculate that? Pressure 1 divided by RT1. True? You tell me if you like it. Okay. How about this one? P1 molar mass of dry air divided by R bar T1. You like it? Yes. Get good at this, okay? Get good at it. You don't need to make errors on this. So that's how you calculate rho 1. A1 was given and B1 was given. I think you can finish it out, or do you want numbers? Do you want numbers? Yes. Okay, I got to get my notes. All right. It looks like this turns out to be 2.2099 kilograms per cubic meter, and that the mass flow rate then is equal to 0.5304 kilograms per second. And I know that I have a centimeter squared. I have to deal with that. I think you should be able to handle a centimeter squared on the area. That's 4 significant digits. It's too many. I'd prefer it's just 0.53 kilograms per second. Now we go to the exit temperature for the air. How am I going to find T2? Mass balance, energy balance. If you're at a loss, just think of that. So let's do an energy balance for this control volume. The rate of change of energy in the control volume with respect to time is equal to Q dot minus W dot plus M dot N times its enthalpy plus specific kinetic energy plus specific potential energy minus mass flow rate out, enthalpy out, specific kinetic energy out, specific potential energy out. I think I wrote the equation okay. Why is this term 0? Steady state. Why is this term 0? Adiabatic. Adiabatic, that's right. Why is this term, which I messed up and didn't put CV as a subscript on that W? There is no shaft, and there's no electric. There's no work going across the boundary of that nozzle, of the control volume surrounding that nozzle. All right, these mass flow rates are the same, so I could sort of just rub out this subscript. M dot's equal to M dot. What about the potential energy change? You might even put over here, change in potential energy 0 as an assumption. See that there's no information given about elevations. And typically nozzles aren't big and tall, they just change the speed of the flow. So that those change in potential energy 0. So what do we come up with? Is we come up with that H1 minus H2 is KE2 minus KE1. All right? So this is C sub P T1 minus T2 is equal to KE2 minus KE1. This is T2 is equal to, I still don't like the way I wrote it, but kinetic energy 2 minus kinetic energy 1 divided by specific heat, C sub P, plus T1. Try to work as far as possible in symbols, because it's easy to fix an algebraic error if you do have an algebraic error. Did I make an algebraic error? Do you like it? At this point, you can't always do this, but at this point, I'm ready to substitute numeric values plus units for what I know. So the kinetic energy is 1/2. What is the speed at the exit? 180 meters per second squared. I'm going to grab that meter squared, second squared, put it out here on the units. Minus, for the kinetic energy 1, 30 squared. So I just handled the numerator, KE2 minus KE1, lowercase specific kinetic energy. It's 1/2 B squared. I divide by the specific heat of the air, 1.02 kilojoules per, and I'm going to put kilogram Kelvin up here. I'm going to flip that up into the numerator for the units. All right, plus I have a temperature coming in, 473 Kelvin. So that's what T2 is. I just have to make sure my units work. There's a favorite unit conversion factor that I need to employ right in here. That unit conversion factor is that a kilojoule per kilogram is 1,000 meters squared per second squared. This is a great unit conversion factor. Well, I've kind of flipped a lot of stuff around, haven't I? Maybe I need a negative right there. Oh, you guys let me get away with the error. Thank you for correcting me. I thank you for doing it gently. You're going to work well with your boss. And not only if you work well with your boss, you'll end up working well with your spouse, well with your neighbors, well with everybody that you're around, if you just treat them with kindness and gentleness when they make a mistake. Maybe you'll be a great parent. Your children make a mistake, you'll treat them gently. Right? There you go. Or maybe when your parents get older and they make a lot of mistakes, you'll be a great son. You'll treat them gently. So there you go. Thank you so much, because now this temperature, T2, oh boy, I calculated 185 degrees C. So yes, it is lower temperature. I do need that negative sign. I don't know why, but in my notes I'm cleaner and neater. But when you're up here doing it in front of people. Okay, add 273 to this and you get 458. But you see how we got the temperature. It's an energy balance. So our next problem is an adiabatic steam turbine. There's a lot of different types of turbines. Hydraulic turbine, steam turbine, gas turbine. In your mind, think about that. Read the book. Hydraulic turbine, steam turbine, gas turbine. This is just a steam turbine. Often we just draw it like this. Here's our steam turbine. Why do we draw it like that? Because it goes through a sequence of expanding, rotating rotors, stators, pushing blades, and then rotating shaft. And out here comes a rotating shaft, some shaft that cuts across the boundary of a control volume that surrounds that steam turbine, and steam comes out down here after it's expanded. You can look at pictures on the internet or even in our textbook on steam turbines. So it's an adiabatic. Sometimes we'll draw this, hashed marks, indicating insulated. No heat transfer. Steam turbine operating at steady state with one inlet, one outlet. Inlet conditions are, we'll call this state 1 coming in. Pressure, let's put it down here. Pressure 1 is equal to 10 megapascal. And temperature 1, did they tell us the temperature? 440 degrees C. And speed 1, 80 meters per second. And the outlet conditions over here is state 2. The pressure at 2 is 10 kilopascal. And the quality, I'm going to put an X over here, is 92%. And the speed V2 is 50 meters per second. And the steam mass flow rate, I'm just going to tuck that up over here, m dot is equal to 12 kilograms per second. I purpose to leave a space for T2, kind of aligned with T1. Okay. I read the question, what is the change in the kinetic energy? So they're asking for delta KE, lowercase ke, specific, change in specific kinetic energy. That's what I'm looking for. Okay, the turbine output power. I'm looking for W dot out of the control volume, or sometimes W dot shaft. Let me draw that. W dot shaft, okay? What is the inlet area of the turbine? A1. That's what I'm looking for. A1. The inlet area of the pipe feeding the turbine. If I want to find the change in kinetic energy, the change, this delta symbol, is always something like the exit or the final minus the initial or the inlet. It's always 2 minus 1. The second minus the final minus the initial. That's your change. If you ever had out of numerical methods, delta x, it's x2 minus x1. Delta t, it's t2 minus t1. That notation is common throughout engineering. So this is equal to 1/2 the speed 2 squared minus speed 1 squared. I sometimes will do this. I'll say, oh, you know what? V1, I know. I'm almost ready to substitute numbers. Hey, V2, I know it. I'm ready to substitute numbers. I have an equation with symbols. I substitute numbers. V2 is 50 squared. V1 is 80 squared. That seems weird that it's coming out slower. It shouldn't come out slower, but hey, let's just run with it. And that's meters squared per second squared on the units. And then I use my conversion factor that 1,000 meters squared per second squared is precisely a kilojoule per kilogram. And whatever I run on that, it's a negative something, 1.95 kilojoules per kilogram. That's the change in the kinetic energy. After you solve a number of these problems, what you start to notice is unless there's a huge change in the speed, the change in kinetic energy is often negligible in a lot of problems. And that's what they're trying to point out with this problem. Negative 1.95 is going to be small relative to other numbers. What about the turbine output power? How do I solve that? Go back to this control volume, apply the first law, conservation of energy, or energy balance for that control volume. It's steady state. Can I tuck it in here maybe? It's steady state, so I'm going to have 0 is equal to 0 minus W dot shaft plus the mass flow rate of the enthalpy coming in minus the enthalpy going out plus the kinetic energy coming in minus the kinetic energy going out. And there's no mention of change in potential energy. If you wanted to make a little assumption list, changes in potential energy are 0. I tried to clean this up a little bit. So the shaft power, what I'm trying to calculate is mass flow rate times H1 minus H2. And now look at, there's a minus sign delta KE on, because I already calculated delta KE. I pause. I ask you, did I make an error? It's okay. And once you start looking at it, it's the steam is coming in with a lot of energy. H1 is going to be high because it's going to have to convert some of that fluid energy into shaft energy. See? So H1's high. We go to our steam table and we look up H1. So H1, maybe even I didn't leave room here, but I can look up H1 knowing this pressure and this temperature. 3213.2 kilojoules per kilogram. All right, how do I get H2? It's this pressure and quality X2. You remember the equation? HF plus the quality HFG. 2 is 2393.2 kilojoules per kilogram. So I have this one, property evaluations, this one, part A, the mass flow rate, 12 kilograms per second. I got it. I'm finally ready to substitute numbers. So W dot shaft equal to 12 kilograms per second. Then I have this change in H, and I get W dot shaft. Notice this is a huge difference. That difference, you could almost just neglect the negative 1.95. Okay. And I get around 9.9, somewhere in that vicinity, megawatts. The kilograms cancel, and I'm left with kilojoules per second, and there's a bunch of them, so I divide by 1,000 and I get megawatts. Or you could put comma 00 kilowatts. The last one, what's the inlet area of the turbine? Well, the mass flow rate coming in, area of the inlet turbine, the speed at the inlet divided by the specific volume at the inlet. I get the specific volume at the inlet knowing the pressure and the temperature, 0.02911 meters cubed per kilogram. I then can solve for the area of the inlet mass flow rate, specific volume divided by the velocity, and I'm running out of room, and it's around 0.00437 meters squared. So let's review. I had to just know what the kinetic energy was to calculate the change in the specific kinetic energy. Notice our unit conversion factor, very useful. I had to go back to the first law for part B and look up properties, enthalpy out of the tables, and watch unit conversions, and there you go. For part C, this is a continuity or conservation of mass, or how velocity, specific volume, cross-sectional area are related to mass flow rate. We use that a lot. All right, and so thank you for those that gave me this number calculated to 3 digits, right? Thank you. Let's move on. So now let's talk about a compressor. A compressor is a work-consuming device. You have compressors in your air conditioning system. You'll have air compressors for just compressed air in the shops. What do you need to use to blow or inflate your tires, your automobile tires and other things? There's a lot of air compressors around, even with a little fish pump, the air pump, right? That's somewhat of an air compressor to blow bubbles in your fish tank, like an air pump. But a compressor typically has a notion of high change in pressure across it, or instead of a pump. Let's go through it. So we have a device. You can just throw it as a box. Here's my compressor, and it's adiabatic. Often we put this notation, hey, that's insulated, Q.0, adiabatic. It intakes refrigerant 134A, and it's state 1 is the intake, inlet, state 2 is the outlet. And it's saturated vapor. Saturated vapor coming in. All right. Its temperature coming in is negative 24 degrees C. And the mass flow rate, I'm going to put it up here, is 1.2 kilograms per second because this thing's going to run at steady state. And the inlet mass flow rate is equal to the exit mass flow rate. Forget the subscripts on MDOT. The exit P2 is equal to, maybe I should line that up, put it down here. P2 is equal to 0.8 megapascal. And the temperature T2 is 60 degrees C. Determine the power input to the compressor. So I know that I'm going to abandon my sign convention or change it up, but I'm going to put W dot into the compressor. And I'm going to put it positive in my energy balance. Don't put a negative in front of that W dot. Because just like Q dot positive in, because my sketch has it positive in, included as a positive power in. Well, so we want to calculate the power input to the compressor W dot C, and I expect a positive answer. What is the inlet volumetric flow rate? AV, put it in parentheses, 1. That's what I'm looking to calculate. AV in parentheses 1. Nice notation for volumetric flow rate coming in. Introduce a control volume, and I can do conservation of mass. We did it. M dot's just equal to M dot. I can do conservation of energy and get some equations. And because I'm looking for this power, probably that's the way I'm going to get it. Energy balance. So if I do that, let me give you the full-blown equation. The rate of change of energy in that control volume with respect to time is equal to the rate at which it flows in with heat plus the rate at which it flows in with shaft work cutting across and feeding that compressor, plus the rate at which it flows in with mass, bringing with it its enthalpy 1, but it goes out also, taking with it its enthalpy going out at 2, coming in with the kinetic energy 1/2 V1 squared, but it also goes out with the kinetic energy V2 squared, coming in with GZ1, going out with GZ2. Steady state, adiabatic. What about changes in kinetic energy? Anything here indicating that something about speeds? Not really. And sometimes you have to read the problem 3 or 4 times. And then sometimes you just have to say, I'm going to assume that the kinetic energy changes are negligible. And when in doubt, put a little assumption box and say changes in kinetic energy equal to 0. That's an assumption. If you want to revise that assumption later, you could come back. How about the change in potential energy? And maybe you put over here is equal to the change in potential energy. So that you kind of in a very compact way declared that is what you're going to be doing. You're assuming those. You mean that this W dot compressor is just the mass flow rate times H2 minus H1? That's it? Well, I switched the order of the H's. Is it good? Okay, I think it's okay. Now we go and we say, I need to get these enthalpies. So I'm looking for enthalpy 1. It's the refrigerant 134A. It's saturated vapor at negative 24 degrees C. And you have to be able to get that enthalpy. True? When we look up that enthalpy, we find that it's 232.85 kilojoules per kilogram. It's H of G at that temperature. Enthalpy of 2, all right? It's the enthalpy of the refrigerant. Get in the right table. Don't go to propane or ammonia or steam or anywhere else. Get the refrigerant 134A. And it's at a temperature of 60 degrees C and a pressure of 0.8 megapascal. It's superheated. So superheated table, you find it's 294.98 kilojoules per kilogram. The mass flow rate was given up here. So now we can calculate W dot C, and we find that it's around 75 5, well, 74.6 kilowatts. What about part B? The inlet volumetric flow rate. The mass flow rate is equal to the volumetric flow rate, AV, divided by the specific volume at 1 inlet. It's also equal to the volumetric flow rate on the outlet divided by the specific volume at the outlet. But we're interested in the inlet volumetric flow rate, so AV at the inlet is equal to the mass flow rate times the specific volume at 1. Our mass flow rate 1.2 kilograms per second. Just like you looked up the enthalpy at state 1, you have to be able to look up the specific volume at state 1. It's V sub G, so 0.1728 meters cubed per kilogram, and you get the volumetric flow rate 0.207 meters cubed per second. That's fine. As long as you have a sketch, and often if you say you got negative 75, you can say, oh, this negative sign is showing me that it's really into the control volume. The power's into the control volume. Ready to work another problem? Refrigerant 134A is throttled from saturated liquid at 700 kPa to 160 kPa. What is this throttling? Well, you come along in a pipe or a tube and you hit a restriction, and often you put this symbol for a valve. And maybe if that valve is controllable, you put a little handle up there to indicate that it can be controlled. Even if it's not manually controlled, maybe it's got a solenoid that controls it, that screws something in, turns a shaft, rotates it out, but it could be controllable valve. Well, this is a restriction as well, this symbol like this. And what it says was it's like a blockage. It's a restriction, okay? Like a partially closed valve would be. Now, we're bringing in refrigerant 134A. The state 1 is the inlet, and state 2 is the outlet across this restriction, this throttling device. Let's just sort of start listing. What is P1? Oh, it's 700 kilopascal. What is P2? It's 160 kilopascal. Let's take a look at temperature. Sometimes it's good to just list all your properties that you know from top to bottom. T and P and V and U and H and S and any others. I mean, there's some others, but these are the more general ones that are applicable. Now, we haven't gotten to entropy, so scratch it off. Okay? And we're going to do a control volume analysis where it cuts around like this. This is my control volume around that valve. All right? Okay. One of the questions is, the first question, what is the inlet temperature? They want me to find T1. What is the exit temperature? They want me to find T2. And what's the exit specific volume? They want me to find V2. So here, this is what I'm looking for. This T1, T2, and V2. Okay, I'm armed with the tools that say conservation of mass, or mass balance says that the mass flow rate 1 is equal to mass flow rate 2. They didn't give me an area, they didn't give me a mass flow rate. Looks like a dead end, doesn't it? That's okay. You applied to conservation of mass, it didn't bring us anything. But let's go to our energy balance. For an open system, one inlet, one outlet, it's running at steady state. Is there any heat transfer from this throttling device? So we could sometimes put little hash marks. It's adiabatic. Its purpose is to restrict the flow, not to, let's say, transfer heat from the device to the surroundings. Okay? Is there any shaft work? No. So we write our energy balance, steady state, no heat transfer, no shaft power, and we have just one flow rate coming in, m dot. It's bringing with it its enthalpy, taking out its enthalpy, bringing with it its kinetic energy, taking out its kinetic energy. bringing with it potential energy, taking out potential energy. Guess what? I'm going to assume the change of potential energy is 0 because there's nothing about the change in elevation. This is a small device. It's not tall. So you can make that assumption as well. What about the change in kinetic energy? Any information about the change in kinetic energy? It's not like a nozzle or a diffuser. Okay. What did the energy equation give us? That H1 is equal to H2. It seems like a dead-end conclusion, but it's a very significant conclusion. This device is not the flow through it, if you look at temperature 1 and temperature 2, is it isothermal? Is it temperature 1 equal to temperature 2? No. Is it isobaric, saying the pressure is the same, inlet and outlet, the same pressure? But it's isenthalpic. Isenthalpic, a new word. Meaning the enthalpy in is equal to enthalpy out. It's not isochoric, not isobaric, not isothermal, it's isenthalpic. So that means the enthalpies are the same. Let's do this. Look again. It was saturated liquid coming in at 700 kPa. Can I get H1? And H1 is equal to H of F at 700 kPa, true? All right. Once I have H1, can I get H2? It's the conservation of energy said it's isenthalpic. H2 is H1. Is enthalpy a intensive property? Enthalpy, specific enthalpy, is it an intensive property? The state principle that we use over and over again in thermodynamics says 2 independent, intensive properties fix the state. Do I now know 2 independent, intensive properties at state 2? They are this one and that one. Pressure and enthalpy. Oh, this is brand new for you. Your brain is probably hurting. 2 properties. I like to be temperature and pressure to fix the state. I'll go get U's and H's and V's and S's and everything else. But this time, P and H fix the state. Pressure and enthalpy fix the state. Does that mean that I can go get temperature at state 2 knowing P2 and H2? That's exactly what it means. That's what we mean by the state principle. I would like to get one of those other properties knowing 2 other properties. I'd like to know temperature as a function of pressure and enthalpy. So let's put some numbers to this just to help flush it out. If it's saturated liquid coming in at that pressure, you know what? I could have answered this question right away. T1. I didn't answer it. What is T1? T sat at the pressure P1, and so we find that this T1 is 26.7 degrees C. Boom, done with that. What is the exit temperature T2? That's the one that I was working on. Well, if I know pressure and I know enthalpy. So this enthalpy, H1, is equal to 86.78 kilojoules per kilogram. H2 is 86.78 kilojoules per kilogram. And how can I find T2? I'm going to pause and let everybody work on that. I'm going to continue on. All right, this is a real challenge, enthalpy and pressure to get the temperature, to fix the state. And I think a lot of people looked at this pressure. And at that pressure, they said, you know, I'm going to look up H of F at the pressure P2. And I'm going to look up H of G at the pressure P2. And then I'm going to see if this H2 falls over here, somewhere in between here, or below here. And if it falls somewhere above Hg, what can I conclude about the state of the refrigerant? It's superheated. Superheated. If H is between H of F at P2 and H of G at P2, I can conclude it's two-phase, a mixture of some liquid and some vapor. And if H2 is below H of F at P2, what can I conclude? It's two names for it, subcooled liquid or compressed liquid. But it's below saturated liquid, right? So it's either subcooled liquid or compressed liquid. It's just your naming. Okay. So what we did was we found that this value is what, and this value is what, and yes, H is between them. I forget the numeric values. So what is the temperature at state 2 then? It's the saturation temperature at 160 kilopascal. So the temperature 2 ends up to be negative 15.6 degrees C. Now, I know that when you're solving engineering problems, I did the same thing. A lot of homework problems. You just like, oh, got it, box it, forget about it, move on. But stop, pause, and think for a minute. I've had refrigerant. It comes into the system at 26 degrees C. The system is a magic black box. I only heard about throttling devices just a few minutes ago. It's a magic black box. The refrigerant comes out of that system at negative 15 degrees C. Somebody want to tell me, can you grab a hold of 26.7 degrees C and hold your hand there for a long time? It's going to be warm, isn't it? Going to be warm. You can feel it. Can you grab negative 15 degrees C and hold it for a long time? No, it's going to be cold. That's really cold. What is that change in temperature? That delta T, that change in temperature, is 42 degrees C drop. There must have been a whole lot of heat transfer. Otherwise, I'm not going to get a fluid to drop its temperature 42 degrees C. That's 70-some, almost 80 degrees F temperature drop. There must have been a whole lot of heat transfer. Was there any heat transfer? No. Thermodynamics is great. I don't trust it. I don't believe it. But somehow it's super. Is this real or is this just made up stuff? It's just made up stuff. I can bring a refrigerant in, black box, and then it comes out cold. I'm glad that I learned that in thermo, but I don't believe it. No, this is really how refrigeration and air conditioning systems work. And I'm sure the person who started and developed it was a genius to begin with. And I'm sure a lot of skeptics, they say, oh, you can't do that. Anybody knows that you cannot bring in a substance that's hot and not have a heat transfer and then bring it out cold. Go back and crawl into your, laboratory or your whatever, but you're a joke, ha, ha, ha. Goddard, when he started shooting missiles up in the sky before World War II, people made fun of him. He was a university professor, I think, at Princeton. And they said, Goddard, you can't get a rocket to go faster than the speed of sound. Any idiot, the little kindergartner can tell you that. The rocket has to push on something. And it can't push on air faster than the air can move away from it. Can you go above? Can you get a rocket above Mach 1? Everybody here is like, oh, she easy. He was mocked. He was mocked in the local newspapers. Goddard was. We have a whole national engineering lab, the Goddard Space Center, true, named after him. So don't bypass that fundamental fact that, wow, this is incredible. Now you're ready to cool something. Put it into an evaporator and you have a refrigerator. You have a freezer. Now the last one, what was the specific volume? V2. Well, the specific volume V2, I first get the quality at state 2 by H of 2 minus H of F divided by HFG. Now I got the quality. at state 2. And then V2 is V sub F plus that same quality times V sub G minus V sub 2. You've got to jump back and forth through these calcs. Like, okay, it's two-phase, I'll get the quality, okay, using enthalpy, now I'll get the specific volume. True? The specific volume at state 2, 0.0342 meters cubed per kilogram. V sub G minus V sub F. V sub G minus V sub F. Thank you. Call it a day. Thank you very much.